color interaction. So in order to talk about color interaction, we talked a little bit about it, prior, but really the idea is that when we look at one color and we see another color, we have interactions of color and we have interactions of light and color. And so one of the people that is responsible for some of the research around this, we can go all the way back to this guy, Michel Eugene Chevreul, and he wrote a book about simultaneous color contrast in the early 1800s, and it ends up getting translated, very bad translation. He's French, of course, and gets translated to English in 1854. And here's an original of that. And there you can see, if you look here, you see how you have different colors next to different colors, and how some of the colors have black behind them, how they appear more vibrant. Like the red appears more vibrant when it's against black than when it's against white, and so on. And depending on what color is next to what, you're going to start to see, the colors change. So here's another illustration from his book, and you can see it's the same exact design that's printed over these background colors, and they look different depending on, the blue looks more vibrant, like against the orange, than it does against the dark violet that's down at the bottom, right? So you can see how, depending on what is next to what, it really can change the way that you perceive that color. So through observation and experimentation and manipulation, basic color demonstrations practiced on his co-workers and customers, Chevreul identified his fundamental law of what he calls simultaneous contrast of color. In the case where the eye sees the same color, sees the same time at the same time two contiguous colors, they will appear dissimilar, both in their optical composition, in other words, their hue, and in the height of their tone, so that difference between white and black. So what we're going to do is I'm going to set my timer, and we're going to look at the black dot in between the colors. So I'm going to get my stopwatch out here, and so I want everyone to just sort of put everything away, don't think about anything, and see the orange circle and the blue circle. And I want you to just look at the black dot and start looking now until I tell you to stop. And so don't think of anything else. Don't move around. Don't look anywhere else. Just keep looking at that black dot. And keep looking and keep looking. And you probably start to notice like some vibrational things happening outside of the colors, but don't pay attention. Just keep looking at the black dot. And don't look away, just keep looking at the black dot. Okay, now look at the other black dot. What did you see? You can go ahead and turn your mic on.
The same, the picture, the dots on the side.
Yeah, so you retained that color, and then when you looked at the white, you still saw that color. So see what I'm talking about? How that kind of stayed with you. So it fatigued those cones. So
I have a question.
Yes.
Did you guys see blue circle, orange circle, or orange circle, blue circle?
I saw blue orange. I thought that was
surprising. It reversed it. Yep.
Yeah.
That's exactly right. Very good. So that's because of the fatiguing of your rods and cones. So it fatigued the orange and replaced it with the blue, fatigued the blue and replaced it with the orange. It was really interesting. So we have simultaneous contrast, which appears in two colors viewed side by side, which was familiar to painters since the Renaissance. And then we have successive contrast, more commonly called negative after image, which is that idea of the light, the light bulb and that kind of after image that you see when you look at a color. So we just saw an after image, right? And then mixed contrast, which appears when two colors viewed together are one after the other. That is, the second color is mixed with the negative after image of the first color. So that's where, like we said, if you looked at the yellow couch and then you looked at the red couch would start to look more orange. So when we look at simultaneous contrast, like for example in this image, what we see is that gray square in the center of each group is exactly the same gray. Now it doesn't look that way, does it? No, because what's around it automatically changes the way that you see it. So if we look at the first one, because that's a lighter tone, it tends to look like the last one is like a reversed. But the reality is those grays, I mean, and on a computer it's kind of hard because there's actual cards that do this, but you'd actually, those grays would be the same. So let's look at another one. So in this one, we're going to look at the middle image. So we're going to stare at the multicolored circle for about 20 seconds, and then we're going to look over to the white. So we're going to do the same thing like we did before, and everyone get, ready, kind of get ready. And okay, let's begin. And we're looking at the center of the color wheel, not the white or the blue, just the center of the color wheel. And we're just going to keep looking at it. Don't look away. And just keep staring at it. Try not to blink. And just keep looking and keep looking. And don't look away. Okay. Keep looking. And now look to the white. What did you see?
Craziness.
What was
It
crazy?
flipped again.
It
But it flipped vertically this time.
Yes, exactly. Okay. So let's kind of give it a rest for a minute. And then we're going to go back and we're going to try it one more time. Okay, is everyone ready? Take a drink of water, look up at the sky, ceiling, just kind of look away. All right, let's take a look at that. Let's go back to that multicolored image in the middle and keep staring at it and keep staring and don't look away. Just keep staring. I'm doing it along with you because sometimes I forget. Keep staring. Don't look away. We're almost there. Keep going. Keep going. Okay, now look at the blue. Did you see the yellow in the bottom?
Mm-hmm.
And mixing.
Yeah.
And this time it mixed with the blue, didn't it?
Mm-hmm.
Yep. So that's where, we just talked about a second ago, the mix contrast. Okay. So I just like to give you actual demonstration because I think it matters. So we did all of those. So Chevreul claimed to predict the visual effects of a simultaneous contrast across all three of these situations with a single rule. If two color areas are seen close together in space or in time, each will shift in hue and value as if the visual complementary color of the neighboring or preceding color were mixed with it. So it's really important. So now I'm going to demonstrate that because that's like a mouthful, right? That's like kind of a lot to accept. So let's take a look here and see if we can get this to work.
Okay, so we're going to create the color after image in your brain. What you need to do at this point is to stare at the dot in the center of the photo and keep staring at the dot. Don't move your eyes, keep staring at the dot. The photo is strangely colored, that's all to do with the demo. So just keep staring at the dot. And in about 20 seconds time or so, the photo is going to be replaced by a black and white version. But you're going to probably see some color in that photo. So keep staring at the dot. That's good. Don't move. Keep staring. There we go. If you move your eyes quickly off to the side and then back to the dot, you should see the black and white photo, and then the colour should reappear when you get back to the black dot. Probably starting to fade now.
Okay, I'm going to
You're all
stop. How many people saw that?
I did.
Yeah, I did.
Yeah,
That is
was wild.
so
That's
insane.
cool.
That was crazy.
Yeah, so basically he put a black and white image there, but what did you see?
Color.
We've seen it in color.
Yeah, let's do it again. Okay, that's why I was like doing this one twice because I just think it's so cool.
That's what my brain just
We're going to create the
did.
colour after image in your brain. What you need to do at this point is to stare at the dot in the centre of the photo and keep staring at the dot. Don't move your eyes, keep staring at the dot. The photo is strangely coloured, that's all to do with the demo. So just keep staring at the dot. And in about 20 seconds time or so, the photo is going to be replaced by a black and white version. But you're going to probably see some colour in that photo. So keep staring at the dot. That's good. Don't move. Keep staring. There we go. If you move your eyes quickly off to the side and then back to the dot, you should see the black and white photo, and then the colour should reappear when you get back to the black dot. Probably starting to fade now. You're all probably familiar with the idea that a TV screen makes colours using red, green and blue pixels at each point. Each colour we see is a particular mixture of these colours. Our eyes aren't TV screens, of course, but they do contain 3 types of colour-sensitive receptors known as cones. One sensitive to red wavelengths of light, one green and one blue. So the way the brain sees different colours is by looking at the relative activity across 3 types of cones. So, when you stared at the strangely coloured building, you are in fact tiring out or fatiguing the 3 types of cones in different ways across the photo. The area of grass was painted mauve, for instance, and this fatigued the red and blue cones that have a view of the grass more than the green cones. When we now replace the strange photo with a black and white photo, we are in fact seeing colour created by different levels of fatigue in each of the cones. The brain only knows about different colours by looking at relative activity across the 3 types of cone. Remember I said if you moved your eyes when looking at the black and white photo, the colour after image disappears? Well, this is interesting because this tells us that the structure of the scene you use to see the after image must be similar to the structure of the scene you use to tie
This is
the
about the
cones out
time and
with.
space.
Any old building won't do. And the same building placed in different positions on the retina won't do either. This may explain why we don't see colour after images all the time, because our eyes are continually moving around.
Is that cool or what? So that's what Chevrolet was talking about. It's like if you looked at it for a long period of time, you know, it had to be the same object, right? And then you moved away, and then you could really experience it. And this is without really understanding like how the eye works. This is, you know, almost 200 years ago. I mean, so I you know, when we think about like the science and how he dealt with it, it was really quite ingenious. Which brings us to this artist. His name is Joseph Albers. And Joseph Albers was a teacher at a school that was in Germany after World War I. So after World War I, there was, you know, great destruction, and they needed to rebuild their cities. And there was a gentleman by the name of Walter Gropius, and Walter Gropius was tasked with re-educating people in art and design. And so he decided, you know, he built this school called the Bauhaus, which literally meant to build a house. And the basic function of the school was based on everything that they needed to do to get their infrastructure and their homes and get everything kind of rebuilt again. And so Joseph Albers was one of the teachers there, and he studied painting in color and color theory. And so he was just a really interesting guy. And you'll see his paintings are very boring, but I think if you understand what he was trying to do, they are not so boring. So let's take a look here. Here's a little bit about him, maybe.
Joseph Albers is an extraordinary figure in the history of not only 20th century art, but 20th century art education. We have archival video of him at Yale at the School of Art, teaching his students, instructing them, and you can see his energy and see the students' kind of raptness in following him along, almost like he's a Pied Piper. He was also very much about experimentation, and he says that even if he knew the right answer to his students' questions, he wouldn't give them the right answer because he would then deprive them of finding the answer for themselves. It was actually after he had retired that Interaction of Color was published, and so he had existing students working on making the silk screens with him and Norman Ives, which the whole thing was printed at Yale. They developed all kinds of new and innovative inks to create these luminous silk screens that were in the original edition. The idea for the Interaction of Color app, I think, in a way actually came from Joseph Albers because of the way he organized, very carefully, very thoughtfully organized that original project. It actually translates beautifully to iPad form. We very carefully chose not to reinvent the design, and so looking at the text on the iPad is very similar. It's the same font, it's the same text column, it's Albers' design, and there was no reason to change that because it's beautiful. So anyone who's familiar with the book can see that we kept the same design sensibility, which was very important to Joseph Albers. Everything behaves like cut paper. So you can now move these pieces to see that they are in fact the same. In addition, the flaps function digitally. But another function that's very important is you can create your own study.
So see, the greens are the
Here's our
same.
palette. Let's see. So it's just like having a desktop, really, that you're covering with stuff. You can see how amazingly that works. I think one of the things that's so beautiful and alluring about working this way is that there is this constant sense of magic and discovery and inspiration, which is not only something that's embodied in this project, but it's very much a part of what Albers wanted to impart to his students.
So there you saw how when he put one color next to another, even though it was the exact same color and they were like, you know, you could see the green against a red or a green against the blue, the green looks different because it's against that other color. So it's the same kind of thing that we're seeing right here. Like we have it against this gray, is the same gray as this, but against here, the white, it looks much darker than it looks against this other tone of yellow. So that's pretty much, you know, he ended up, he started the Bauhaus School in 1923. He left in 1933 because the Third Reich had come in and, you know, pretty much closed down the school. He came to the United States to get away from the Nazis. And then he taught at Black Mountain College, 1933 to 1949. And then he was the head of the painting and color theory at Yale University from 1950 to 1958. And then after that, he retired. And he wrote this book called The Color of Interaction. And they have made it at 75-year anniversary, or 50th year, I'm sorry, 50th year anniversary, they made it into an iPad app, which is just, you saw it in action. It's really pretty cool.
Art is not an object, but art is an experience.
We actually innately know about colour. It's a little bit like swimming. You've just got to jump in. Hopefully someone's there like your dad to catch you. The same with colour, just jump right in, because then you'll begin to find your own voice.
You know, color as subject matter, I mean, you can just use color as subject matter. Like this is going to be about red, blue, green.
I know that everyone needs a little bit of color in their lives, and a little bit of pop can bring a smile to their face, can sort of brighten someone's day.
Most of the clients that I do work with, you know, look to me to sort of provide the color direction.
Color is one of the earliest components of the design that I address, mainly because color has so much power to establish mood, tone, perspective.
When you're doing patterns and when you're creating something, it's most interesting to see what you can do with the color.
I think of myself first and foremost as an architect. But when does color enter the design process? Intrinsically, probably very early on.
Trust your own instincts, I think, is a really, because everybody's going to have a different sense of what they respond to and what feels right.
Color is really the mise en scène in which everything else takes place.
You know, what I think is so sort of brilliant about the Albers interaction of color is that that brings that problem out and brings it into perception and brings it into the visual and makes that kind of manifest. So it's a really great way to get students to think more philosophically too about, it's very pragmatic on the one hand, but it gets them to think about what's at stake in making art.
So that's really the aim of this. It's not to become an Albers painter, but to find out who you are in relation to colour.
You may remember that I often had said, even if I would know the answer to your question, I would not give it to you, because then I deprive you of finding out it yourself.
So the whole idea here is that we want you to discover your own sense of color. So here we have, and I'm just going to go through these a little quickly, but these are some of Albers' these whole series of squares where he would put one color against another, against another, against another to see like what the kind of optical illusion or like what kind of vibration would happen, what would push forward, what would pull back, you know. So this whole idea of like, how do you make something look like it's more in the foreground? How do you make something look like it's in the background? You know, how does one color look next to another? So in this case, you know, we've got, you know, this series of kind of really simple, but when we look at this one, we start to see how the blue red, that darker red against the blue almost has a vibrational effect. You know, just like when we were staring at those other colors, we start to see, you know, sort of a problem because it's vibration, you know, it's so opposite on the color wheel. So what are the principles of color interaction? We have light, dark, and value contrast. So light and dark, and the value, if it's at white, or if we've added gray, or whatever, you know, whatever value it's in, those contrasts matter. Number 2 is the complementary reaction or effect. So that's like the opposite ends of the color wheel. And then the third would be subtraction, where it feels like we're like cutting out a piece of the color. So let's look at, here's light and dark, value contrast. So those 2 squares in the center are the same, but they tend to look different depending on what's next to them. And if I put them in grayscale, that's what they look like there. So it's the same exact thing, same exact slide, except I put it in grayscale. So let's go back and look at it one more time. And then in grayscale. So see how that gray just tends to look lighter against a dark background, and now it looks darker against a light background. So it's all about interaction. Here's another one. Really great, like that yellow starts to appear almost golden against that really bright fuchsia. So this is complementary reaction. You know, remember we talked about the yellow and the violet furniture, right? In the very beginning. And so there you can see what happens with that color when you break it down. Here's another complementary reaction. And there you can see where it's, you know, really close to the other color, it tends to look quite different. And then here's our subtraction. And we'll do one more. All right, so let's take a look at optical mixtures. What are they? So this is a painting that's in the Chicago Art Institute, and it's the Luncheon on the Grass by Seurat. And Seurat was what we call a pointillist. So basically he was a mathematician, he started doing art, and he would take like little points of color, like long before there were pixels and television, and he would put them on, and when we were far away from them, they would blend together. So they would create an illusion of a color. So if we go a close-up of this, there you can see all the little points of color, right? So when we go back, you know, and look at, you know, the imagery, you can see, you know, from a distance, it starts to feel like those colors are blended. Another artist that did that was Chuck Close, and this is the kind of things he would do. So really fun. Here's another one of his images. So let's take a look at how optical illusion works.
So tonight I'm hanging out with my friend Nigel, and he's brought along one of his science toys, a little white plastic ball.
It's not actually a white plastic ball at all.
You told me you were bringing the white plastic ball tonight.
It's, what color would you call that?
I would call it purple. It's a purple ball.
Purple, really? You see purple
I'm
there?
not good with colors. I don't know if you want me to say fuchsia, but it's, you know, it's purple.
Well, it's interesting you say that. There is light in there, but it is actually a red, blue, and green light.
But it looks purple.
No, there's definitely a red, blue, and green light in there.
All right, well, how are we going to settle this debate?
I can show you that it is red, blue, and green.
How are you going to do that?
By twirling it in a circle. Simple.
You're going to twirl that in a circle, and all of a sudden I'm going to see that it's red, blue, and green.
I promise you nothing less.
Okay, that's a pretty good promise. Let's see it.
All right.
Wow. Okay, so I'm not too big of a person to admit when I'm wrong, and I see a red, green, and blue balls around the outside of the circle. But when you slow it down, it goes back to being purple.
Yeah, it's actually, everyone will see it being purple because the red, blue, and green lights are turning on and off so quickly after each other that your brain actually merges it into one color when the ball is in one place.
So the eye actually kind of holds the information there about what color it's seeing for an instant longer than it's there, and it merges together to produce that purple color.
And there's your optical
red,
mixture.
Blue and green kind of merge to this dusty violet color.
Dusty violet?
Dusty violet.
You know your colors, sir.
Yes, should be a painter.
Why can we see them separated when you swirl it in a circle?
When I swirl it in a circle, I'm actually getting the ball to switch colors to red, to green, to blue at different points in space. So at different points in space, your eye is not actually holding that image as it switches to a different color.
Right. So even if the eye remembers the color that it's seen, it's not going to merge with the next color because that occurs at a different point in space.
Exactly. So it's much easier to see the red, blue, and green lights happening in the ball than it is when it's still.
So can you think of some practical applications for this?
I cannot.
but it's a lot of fun for a Saturday night out,
It
right?
is a lot of fun for a Saturday night out in a dark alley.
Yeah. So try that at your next party trick.
Yeah, it's a good party trick.
All right. Well, let's
We
go.
go to a lot of parties, as you can see.
Let's go crash some parties. We're going to be a big hit with this thing.
Okay. And so, I hope that, you start to look at color a little bit more, specifically in terms of like the science of it.